Hi everyone, my name is Omkar, and this is my thermal analysis project for PCBs, printed circuit boards, in spring 2026 with Professor Jeffrey Knudsen. So here, if you don't know anything about PCBs, as you can tell, I'm an electrical engineer. It's generally you have a sandwich of different layers, maybe copper foil, a prepeg core, copper prepeg core, or something where you have some dielectric in between copper layers. As you can tell, I have some different core, dielectric, inner copper layers here, which are just modeled as solids, so solid extrusions really. So if I go over here to my layers, you can see that it's a solid extrude. And then I also have an inductor, a surface mount inductor, and a transistor. So the transistor is modeled as a rectangular component. I have some property, so my properties, I have some copper, some dielectric, which is usually maybe like FR4, flame retardant, glass reinforced epoxy laminate, and it has some different material properties such as the thermal conductivity in units of watts per meter degrees C, density in kilograms per meter cubed, and specific heat in joules per kilogram degrees C. So everything I've done is in SI units, but my board is actually in mils or inches. So it's 2 inches by 2.5 inches, and thickness is really different based on which layer it is. I'll go over that later. And then you also have some dielectric, which has some thermal conductivity of 0.3. And as you can tell, this is a lot smaller than the copper. And it becomes important later in how I've meshed things. So those are my components, components, 3D deformable extrusion, and my properties. So the way I've done it is I've created a number of different layers. So I have my copper, then I have my dielectric, then I have an inner copper layer because I'm modeling a 4-layer PCB stack up. Then I have some core, then I have some copper, then I have some dielectric, and then I have a copper again. And then I have my power MOSFET and my inductor on the sides over here. And for my step, what I've done is it's a type heat transfer with some time period. You need to make sure that this time period is large enough that you can reach steady state. So Abacus might not throw an error, but you might notice that your temperature is less than it should be, and that's because you haven't reached steady state yet. So make sure that this time period is large enough. You have some incrementations, so some max allowable temperature, some max emissivity that can be changed. My interaction is pretty complicated. The way I've done it is I've created some net ties so that tie different surfaces together. So for example, the bottom surface of my copper layer, which is my top layer, is net tied to the top surface of the dielectric layer, which is right underneath it. And then the bottom layer of that dielectric is net tied to the top layer of the copper below that, and so on and so on. So I've kind of just net tied all the different layers. You need to make sure that you have to be careful you don't net tie the same surface or something, or Abacus will throw a bunch of errors at you. And then I've also net tied this surface, the top copper surface, with the bottom surfaces of my 2 components. And now that we're in interactions, there's another thing that we have to do, which is set our radiation and set our convection. So if you try to go to your load, your boundary condition, right, you can see that there's no place to set convection radiation. Conduction is done through Abacus, already. It's done naturally through Abacus, so you don't really need to worry about conduction effects. You just set some temperature, some heat flux, and conduction will happen naturally. But for radiation and convection, you have to go over to your model tree and then right-click on interactions, create, and then you'll get this prompt. Surface film condition is for convection that I've used, and surface radiation is for radiation. So you can see convection here I've set for the outer layers, surfaces of my MOSFET. So for convection, you need some film coefficient or convection coefficient, and this is based on what heat flow or like kind of airflow you want on top of your component. So I just assumed still air, so that's why I chose 10. But if you want some forced airflow, then you can go with like a higher number and then I have some ambient temperature. And then for radiation, you have to set some emissivity and then some ambient temperature. And then, as you can see, I've set it on all of the outer surfaces. And based on, which surfaces it is, I've set, a different emissivity coefficient. So, that's there, kind of over there. So those are the interactions. And then the other thing is that this is really important. In the model tree, you right-click on model, edit attributes. You have to set the absolute zero. Again, I'm going with degree C, and the Stefan-Boltzmann constant. The universal gas constant, I've just set, just like that. But you don't really need it. You just need to make sure you have these two in here, or your radiation won't run. And then we can go over to our loads. So the way the loads are, I've just created some body heat flux. So I've just assumed that the component is heating up with some current being driven through it. And then that heat up is kind of creating this heat flux in units of watts per meters cubed. And so for the semiconductor, for the MOSFET, I've done it I squared R losses. So the current squared times the resistance in ohms divided by the volume. For the inductor, it's I squared R losses as well, but I've kind of removed any of the saturation, hysteresis, core losses that are naturally there in inductors, divided by the volume, which in this case is pi R squared H, for a cylinder. So that's how you get this body heat flux. And then you can also set a temperature, which is like a boundary condition, but I haven't set that yet. So I'll get into that later. So that's that. Now we can go to our mesh. And so the way that I've meshed this, I tried to be a little bit smart about this. So as you kind of noticed earlier, there's a distinction between the thermal conductivity of copper and thermal conductivity of the dielectric. The thermal conductivity of copper is much larger, so it's able to remove heat from those hot devices a lot faster. So that has a little bit more elements than the dielectric layer, which I've just set as one element. I'm limited by 1,000 nodes, so there's so much I can do. And then the inductor and the transistor are like much larger element meshes of this type. So you go over here, you make sure you set the element type, heat transfer, and then for the cylinder, I've set wedges, so that's of type DC3D6, which is different than the hexes, which I've set these linear heat transfer bricks, which I've set for all of my other components, because those components are rectangular. So if you see here, and I'm trying to go create my mesh, you can see that I have two different types of nodes. Well, I just have one type of node for this guy, but if I go into my assembly and then I mesh this component over here, you can see I have two different types of nodes. Okay, great. So that's my mesh. Now I have already submitted my job, so we can just go straight to the visualization. So now this is the really important part. The important part is that because I haven't set any boundary conditions, my reaction flux is 0. That's just how it is. My heat flux is based on the components. So the components are relatively, they have relatively the same body heat flux, which is why they're kind of the same color. But then I also have some nodal temperatures. So you can see how the nodal temperatures vary between these. And so it kind of heats up at the top of that inductor. So if we want to see some reaction flux, what we'll do is we can go back to the load. We can create some temperature. And we can set that, let's say that maybe we have some thermal solution. So maybe we have some cold plate or something that we're putting on top of this inductor that we're setting to maybe like 20 degrees C, right? And now from here, we've set that condition and we're going to submit our job again. And when we submit our job again, we get this prompt. I don't know why. You can just say, oh, yes, submit the job. You can monitor it. And then because my durations are very large, it just goes really fast. So you can go to results. And then the results, you can see this reaction flux. And the reaction flux is now non-zero. So you can see it's 0 for this MOSFET because I haven't set any boundary conditions. But for this inductor, this top of this inductor, it's non-zero. So that's kind of how you do heat analysis in Abacus. Thank you very much. This is Omkar Kulkarni with heat analysis of PCBs.